No, I mean, I can just leave.
Yeah, as you wish. Yeah, sure.
It should be fine.
Yeah. Anyway, this is like the main result. And then it's your homework to check that this is a solution indeed. For those who want to leave early. Also, to show that we have had a lot of freedom, this is not the only representation for transformer. So my question, for example, if we consider a function, a very similar function, like this, this formally different function, but also for pi periodic. So now I just put e in the power of e theta, e instead of this constant. And that's a different function for me. But like a question, whether it also will give us a solution. And if yes, why? You can think about it in years per time. It's like a nice simple thing to think about. Like spoiler, yeah, that it is also a solution. And it will not miss the uniqueness, because after we substitute it here, we have some periodicity, and they basically give us equivalent wave fields. And that's something you can try to check. So okay, let's start checking whether it satisfies whether it is a solution to our problem. So first of all, as we said, this thing satisfies the Greenwald's equation because we have a convergent or integral here. Our integrand decays exponentially. Here it also decays exponentially, and here is like a small area where it grows, but it doesn't matter because this area is finite. So here we have some growth, doesn't matter. Oh, it convergent, then it's a solution to Greenwald's equation. So let's check whether it satisfies the radiation condition. So let's study its asymptotics as r tends to infinity. How should we do it? Do you have ideas? Because we did a similar thing for Green's function, maybe at this point you see how to do it here. How you would have estimated this integral? What is the standard way to estimate oscillatory integrals? This, we did it on lecture 1, and this is called a sample point method. So what we will do? We will take this contour and we will deform this contour into a steepest descent contour. So, yeah, probably I should use another color to maybe just draw a deformation. So what we do, we bring these two contours close together and, and deform it like this. So this is still the same contour. The only thing that might have happened, we might have crossed this pole. So it's probably these two contours are equivalent, plus for this particular picture, additional pole. Right? And what do we have for our integral? And also this have in mind that now we don't have 2 pi periodicity. These two contours, they don't cancel themselves. So when we had a usual plane wave, these two contours were canceling themselves, but now our function is 4 pi periodic, so they survive. So we don't have any contradictions and we don't get 0. So we have for r going to infinity. For r tending to infinity, we have, like roughly, I will write it like this. So this one I will, this bit will be gamma minus, and this bit will be gamma plus. So we have 2 integrals for with saddle point contours, for which we can apply saddle point method and get the first term of our asymptotes. And this thing will give us win, which is nice because we expect to, at infinity, our field should be some like directivity pattern here and a plane wave. So that's how we expect our field to behave. And so let's compute one of these integrals approximately, since you don't remember. A little bit. And for the first term, I will write it like this. Here I shifted my variable of integration. So this is not actually this contour, this is gamma minus minus phi. So I shifted everything by phi. So now this function is plus phi, and here it's, I took the phi out. And okay, again, we have this integral. Our integrand exponentially small everywhere basically, except the small vicinity of this point. And this is the saddle point of our integral. So let's expand our phase in the vicinity of this function. And for this function doesn't oscillate. We suppose that this function is continuous, and we know this function. So we can show it that nothing bad happens to it in the vicinity of this point. Then what we do? We write something like this. So this part is just constant, and this bit gives us a Poisson integral square of pi with some coefficient. So course, I computed those coefficients. And nice. And then similarly, we can compute the second term. So what do we get? We get the following structure of our field at infinity. So we have some directivity function. Then we have a cylindrical wave. And here, like this. So this is the scattered field, and of course, in having this form, we can check that radiation conditions are satisfied. So we can check both radiation conditions in Sommerfeld form, where we take a derivative and minus something. Do you remember that? Like a radial derivative minus something is equal to 0. Or we can take a radiation condition as a limiting absorption principle. This thing decays exponentially. But we did this computation, and now we actually have an expression for the directivity of a scattered field in terms of Sommerfeld transform. And I will write it down. Oh, we did one check. Radiation conditions are satisfied. So this is the directivity of the diffraction. It's multiplied by minus 4. Get everything. And probably and remarkably for Dirichlet-Neyman, so this thing is, if we do the calculations, this thing will be 1 over cosine minus. Oh, it's quite a simple expression, which is completely real, which is kind of nice. You have scattering of a real wave, and plus here minus for Neumann this is the directivity for half plane. It's just something we get from this computation out of checking radiation conditions. So I won't say much about boundary conditions, but I mean we discussed it with satisfaction of boundary conditions we get from the symmetric formula. So we have symmetrization. If two waves coming like this, we will have a zero of normal derivative if we choose a sign plus, and we will have a zero of the field if we choose sign minus, and there is nothing more to it. And the most complicated bit is to check mixture condition. And I need to say, Sommerfeld himself, he doesn't check it. Because I think at this point Sommerfeld condition didn't exist. Oh, mixture condition didn't exist. And this is a tricky one. But the thing that Sommerfeld shows that this integral is convergent for r equal to 0, which is also Sommerfeld. Because when it's equal to 0, we don't have an exponential term, and that is a question. I will try to do it with you, maybe, I don't know, I will try to be fast, but maybe it will take another 20 minutes. So, first of all, before we can start, we need some prerequisites from theory of functions. And this is something, if you do diffraction theory, it's something you should know. It's called Watson's lemma. So Watson's lemma states that if we have a function, I won't get into all the details, so I will formulate it in a very rough way, which behaves as a power function. As x tends to 0, then its Fourier image here note I take minus, so it depends on what sign I take. Minus. Then Watson's lemma states that the Fourier image behaves as sine minus 1 minus beta in lower half plane. In lower half plane. Makes sense, because so I have here minus, and this integral converges if psi has an imaginary part. So for any imaginary part, this integral converges. For real psi, it's a question, like usually this integral will also converge. For real psi, because then it will be a usual Fourier transform on a real one. And for more or less nice u, it will converge. But this integral will diverge in upper half plane. So we only consider psi lying in lower. And it behaves like this. It's quite easy to show. So we just substitute this behavior. Since we have exponential convergence, we can get rid of exponentially small terms, like the difference between this one and this one. And then we just estimate this integral, and we naturally will get this behavior. If I have time, I will demonstrate it. But that's one fact. So for half plane, so for half plane, we said that u should behave as what? As r in what power? Do you remember from last lecture? You he doesn't have it. It's only person who have a previous lecture is Thomas. Close enough. Oh, not right. But that's anyway, fine. Okay, you don't remember, it's one over. I mean, it doesn't matter. You should. It's not necessary to remember. But I want you to believe me. So it's not I'm coming with these things from my mind. It's just what we did last time. So we showed that our function should behave like this. So for our case, beta is 1 over 10. So we want to show that the spectral function, and we will get to the point when I will explain what is the spectral function, will behave like -3 over 10. So, as you see, we have some kind of a Fourier looking integral, but not quite. So let's do some change of variables and make this integral look like a Fourier integral. We did a similar thing with Green's function, but we were starting from Fourier integral, and then we did a change of variables, and we got the plane wave decomposition. And I will do a couple of tricks. And I think, actually, there is like no book, I think, where you can find it. Or if you, like, people usually avoid to discuss this. There is some books that mention it, but nobody does it explicitly. So, what I say, I consider the integral only on this arc. So let's call this arc gamma plus, this arc we will call gamma minus. And so let's rewrite this Sommerfeld integral in the following form. But now I want to have this expression like this. Here, since I did the shift, here I have just, so I did the shift again, like previously. And why I have the second term? Because now I want to integrate only along gamma plus. So this thing shifts our contours by 2 pi and reflects it. Cool. And so only we have the upper arc. And then what change of variables do you think I will do? What is psi? What I will take as psi? To get a Fourier integral. So I want to have a Fourier type integral. So what I will use as a new variable?
K.
What?
K.
K?
Yeah.
No, K. So then it will be just X, I, R. So it will be just a Fourier space. So I do this change of variables. And then also similarly to what we have for Green's function, this thing will turn into real line, almost real. It will turn to a line which is close to the real line, slightly below the real line because this thing is slightly above. And you know, this bit always tricky because you need to trace the contour. So I propose you just to check it like either numerically or by doing some simple analysis. But at this point, you can believe it. And it's quite easy to believe. So if I, like not this contour in particular, but if I draw it like this. So for theta between like pi and minus pi, I will get some real values for psi, and for this also. And anyway, we can say that we deformed our contour accordingly. Where this is some where this subparameter epsilon, which is not necessarily small, can be more or less arbitrary positive epsilon. Then we have so I change nothing here. I just I indicate that now theta is a function of psi. So it's like arccosinus, arccosine of psi over k. And I have a square root because of the differentiation of this. So when I differentiate this thing, I get a sine t. And when I express it back in terms of psi, I get the square. But now, luckily, I have a Fourier type integral. And for this Fourier type integral, it lets me draw somewhere the contour, sketch it. Just quickly. So my contour is a line. Yeah, I will go like this. This is my epsilon. And this is my branch point. So this is k. This is minus k. And like, it doesn't matter. I can add small imaginary part. I may not add. And I also have something which gives me the plane wave. I will call it k in. So this is a pole which corresponds to the plane wave. It should be somewhere here. So when theta is equal to theta in. And then, so I have this type of integral, and I'm very close to applying Watson's lemma. But this integral is going from minus infinity to plus infinity, and I want one-sided Fourier transform. I formulated Watson's lemma for one-sided Fourier transform. But let's call it. So we want to formulate some restriction on this function, the Fourier image of u. So let's call all this thing g of psi, and this is just by definition a Fourier image of u. Like a bit shifted, but don't worry about it. So here's some tricky part. There is actually like we can have some problems from this pole, but we may not care about this pole much because we anyway know what this pole gives. This pole will either give us a plane wave if we in the like illuminated area, or it will not, but it's just some constant around the edge of the scatter. So let's care about the rest of the field, about the behavior of scattered field. And that's part which should behave as r over minus 1 over 2. And so formally, g over xi is Fourier transform of a function which is u z r phi for r bigger than 0 and 0 for r less than 0. Do you know why it's 0 for r less than 0? You don't know. Do you have ideas? Because you can take this contour of integration, and for r smaller than 0, we can apply Jordan lemma in lower half plane. So the function is analytic in the lower half plane. And if we have exponential decay, we can close the contour of integration and get 0 for this integral. But that's only true for negative r. That's when we have decay in lower half plane. Make sense? So, from this, we have, I understand it's some, nasty stuff, but I don't see any other way to do it. And it's probably a good illustration of what is, day-to-day life of specialist in diffraction theory consists of playing with this analytic functions. So then by definition, g of xi is given by this one-sided Fourier transform. Correct? Thus it behaves as, so since this thing should behave as r minus 3 minus 1 over 2, for this function, we have a mixing condition, like have a consequence of mixing condition that it should behave like this. So what remains? We should compute this function and check. Because we know this function, we can substitute everything. We can just do like the expansion, the Taylor expansion in upper half plane or even lower half plane, and just check that we have this behavior. So just by expanding this function. And if we have this behavior, then we satisfy mixing condition, and then our solution is good. But now it's quite simple to do, and I will leave it for you as a task. Homework. Homework. So, as theta behaves as E in theta over 2, and HP in lower half plane shown. This is kind of obvious because we have an exponent here, I theta. Show that g of psi behaves as sin minus 3 over 2. So this is the way to check the mixing condition. And that's it. That's like final result. We checked everything and we proved that we have a solution for half-plane problem. So you can go if you want. And like, I have probably 5 more minutes of additional science, and I will let everybody go free. But anyway, thanks for coming.
Thank you very much for coming
I need the toilet, so I might go as well.
Sure.
Thank you,
Sure.
It's really, really interesting.
Yeah, definitely good.
Very glad I took contact.
Yeah? Good. See, we will not have any lectures for next 3 weeks. I will send the email, and if you still, have some interest, we can continue maybe at middle of April.
Sounds good.
Yeah, okay.
Thank you.
Two more things I will mention for you, for those who stayed, if you want.
Of course. Always.
So, what generalizations we have? Obvious ones. So, like, we did a lot of work, and we can have some things for free.
You have low battery.
No battery.
Yeah, this day. Would you like some?
No,
You have 20%.
it's like enough. And so, consider a problem of diffraction by a wedge. With the angle like this. Doing exactly the same thing, we get our Sommerfeld transformant by changing 2 to n. So our Sommerfeld transformant will be like this. This is quite cool. And if you will probably take n to infinity, you will get a model of a perfectly absorbing screen, mathematical model. You can actually take this limit and you will have some expression. This expression is written in Sommerfeld's book. I didn't put it. And yeah, okay, let's final remark is let's show why Watson's lemma holds. Why it holds. So, remark. What's this? They said, so we have function defined as a half space Fourier transform. And U behaves as x beta. So for, first of all, for and psi in the lower half plane, G of psi is regular, and the integral has exponential convergence. So we have an obvious estimate. Just for you to see that Watson's lemma is a simple thing, actually, not something complicated. Of course, with a bit of effort can be short form, but that's very believable, I suppose. Was something exponentially small, because apart from 0, this thing decays exponentially. And okay, let's just like renormalize it basically. So we can write it this integral. We can write it like this. But those who are smart just know the name for this integral. If we have smart people, they know a special function which corresponds to this. But anyway, so we can have this thing. So I just used a dummy variable t equal to xi. And now this expression is just a constant. It doesn't depend on xi. So it's some constant, we can compute it, for example, numerically. It's of course a gamma function. And when we computed it, and we don't care. Thus, just from this narrative, it follows that if we never messed up, it should behave like this. So that's it. Like nothing is smart. But of course, for example, we cannot take b like smaller than -1, then we will not have the convergence. So we have some restriction, but that's kind of the only restriction. So it should be bigger than -1. And in our case, it's 1/2. Not a problem. So that's it. That's it. Thank you for coming and see you next time.